Hello and welcome to this online lecture. My name is Patty Kokish and today we're going to be going through topics from week 11 of your online Math 136 class at Ivy Tech. We're going to start with section 6.1, which is all about composite functions. So let's look at a definition here. Given two functions f and g, the composite function denoted by f composed with g, so this little thing you read as composed with, is defined by f composed with g of x is f of g of x. Now, the domain is going to be the set of all numbers x in the domain such that g of x is also in the domain of f. So the easiest way to do this is to actually look at some examples. So let's go ahead and evaluate some composite functions, and then we're also going to find some domains. So let's suppose that we want to find f composed with g of 1. So what we need to do in this case is we need to take f of g of 1. So the first thing that we need to do is we need to kind of work our way out from the inside. So if you write it like this is a little easier to see. So if you write it as f of g of 1, we need to start on the inside with g of 1. And all we need to do in order to find g of 1, you guys know how to find f of 2 or h of 5. It doesn't matter what the number is, you just take whatever it is and you plug it in for x. So if we're finding g of 1, all you do is take 1 and plug it in everywhere you see an x. So we're going to have 4 times 1 cubed plus 1. And if you actually do this, 1 cubed is 1. 1 times 4 is 4. 4 plus 1 gives you 5. So we know that this red part here, this g of 1, is actually 5. So what we need to do is we need to take the 5 and then plug it in. So now we have something where we're just trying to find f of 5. So if we're trying to find f of 5, this is equally easy. All we have to do is plug 5 in everywhere we see an x into our f of x function. So we have 2 times 5 squared plus 3, which is going to give us, let's see, 25 will be from the 5 squared. 25 times 2 gives us 50. 50 plus 3 gives us 53. Okay, for this one we want g composed with f of 1. So we want g of f of 1. So again, we want to work our way out from the inside. So I want you guys to see if you can figure this out. So I'm going to give you a second. I want you to go ahead and evaluate f of 1 and then plug it back into g. So let me give you about 30 seconds to work on that. Okay, so hopefully you were able to figure out that f of 1 means that we want to take our f of x function and plug 1 in. So we're going to have 2 times 1 squared plus 3. 1 squared is just 1. 1 times 2 is 2. 2 plus 3 gives us 5. And then if we want to find g of f of 1, we take g of 5, since f of 1 is just 5. So g of 5 is going to be 4 times 5 cubed plus 1. 5 cubed gives us 125. 125 times 4 gives us 500. 500 plus 1 gives us 501. And this one, we want f composed with f of negative 2. So we want to find f of negative 2. So we want to start on the inside again. So we want to take negative 2 and plug it in for x into our f of x function. And if you do this, you should have 2 times negative 2 squared plus 3. Negative 2 squared is going to give you 4. 4 times 2 gives you 8. 8 plus 3 gives you 11 here. And then we want to take the 11 and plug that in. So we're finding f of 11. So we take 11 and we plug it again into f of x. So we have 2 times 11 squared plus 3. So 11 squared is 121. 121 times 2 is going to be 242. And then we add 3 to get 245. And finally, I want to give you another minute to try this one here, which is g composed with g of negative 1. So you need to find g of negative 1, and then you need to plug that back into g once you have it. So let me give you, again, 20-30 seconds to figure that one out. Okay, so when you plug -1 into g of x, you should get 4 times -1 cubed plus 3. -1 cubed is still just -1. -1 times 4 gives you -4. And then -4 plus 1 gives you -3. So really what we're finding is g of -3. So all we have to do is take our function, g of x, and plug -3 in. So we have -3 cubed times 4 plus 1. So -3 cubed is going to give you -27. Let's see, -27 times 4 is going to give you -108. -108 plus 1 gives you -107. Okay, now let's find somewhere we have to find the composite functions and also the domain. So let's go ahead and find f of g of x. So we're going to take g of x, which is 4x plus 1, and we're going to plug it in for f of x into our x spot. Okay, so we're going to take g of x, which is 4x plus 1, and we're going to plug that in everywhere we see an x in our f of x. Because really what we're finding is f of 4x plus 1. So we're going to have 2 times 4x plus 1 squared, that's from this piece right here, minus 4x plus 1 plus 4. And we're going to go ahead and factor this out, okay, FOIL it if you'd like, distribute the negative. So we have 2 times 16x squared plus 8x plus 1, and then we distributed this negative, so we have -4x minus 1 plus 4. And then distribute the 2 through, so we have 32x squared plus 16x plus 2 minus 4x, and we combined like terms here. -1 plus 4 gives us 3. And then we just have to finish combining the like terms. We should get 32x squared plus 12x plus 5. Now, the domain of G is all real numbers, as in the domain of the composite function. So the domain of f composed with G is just the set of all real numbers. Because here we just have polynomials, which are just going to be defined across all real numbers. Let's look at g of f of x. So that means we're going to take our f of x function, which is 2x squared minus x plus 4, and we're going to plug it into g. So we're finding g of 2x squared minus x plus 4. So that means that we should take our g of x function, and everywhere we see an x, we're going to replace it by this right here. So we have 4 times 2x squared minus x plus 4 plus 1. So we just need to distribute and combine like terms. So we should get 8x squared minus 4x plus 17. And again, the domain of f is going to be all real numbers, as is the domain of the composite function. So the domain of g composed with f is just going to be the set of all real numbers again, because we just have polynomials. All right, let's deal with one that's maybe a little messier, has some fractions here. So we have f of x equals 3 over x minus 5, and g of x equals 2 over x plus 1. And we want to go ahead and find the domain. So let's go ahead and find the domain of g first. We want to find the domain of f composed with g. So if we look at this, we have g of x equals 2 over x plus 1. Hopefully you remember how to find the domain of this type of function. All you need to do is set the denominator not equal to 0 and solve. So we get x such that x is not equal to -1, so that's going to be our domain for g. So that means that we need to exclude -1 from the domain of f composed with g. So what we need to do is we need to go ahead and find the domain of f, okay? And if you look at the domain of f, you're going to have x minus 5 not equal to 0, so you're going to get x not equal to 5. So if we put g of x into this function, we don't want g of x to equal 5. So what we actually need to solve is we need to solve g of x equal to 5. So we have 2 over x plus 1 equals 5, because 5 is the number that makes our f of x function undefined. So we go ahead and multiply by the denominator in order to get rid of it. So we have 2 equals 5x plus 5 if we distribute. And if you actually solve this, you get x equals -3/5. So our domain is going to be the original number that we needed to exclude, which was -1, because that makes g of x undefined, and also -3/5, because when we plug it in for g of x, it makes our f of x equal to 5, which is no good. Okay, so let's suppose that we have the same functions and we want to find f composed with g. So again, we're noting the domains. Okay, so if we're finding f of g of x, all we have to do is take g of x, which is 2 over x plus 1, and we need to plug it in to f. So really we're finding f of 2 over x plus 1. So this looks a little bit nasty because we have a fraction within a fraction, but that's all right. So we take our f of x function, which is 3 over x minus 5, and we still have this 3 and this minus 5, but now in place of x, we're putting our g of x function, which is 2 over x plus 1. So we have 3 over 2 over x plus 1 minus 5. And then we probably want to make this look a little bit nicer, which would be to get rid of the double fractions. So if we multiply everything by x plus 1, that's going to help a little bit. So if we multiply the numerator by x plus 1, we just have 3 times the quantity x plus 1. If we multiply the denominator by x plus 1, with this 2, with this fraction right here, it's just going to cancel. So you're just going to be left with 2 right here. And then we have minus 5 times x plus 1. And then we go ahead and distribute, so we should have 3x plus 3 over 2 minus 5x minus 5. And then we combine like terms, so it's 3x plus 3 over negative 5x minus 3. And we just go ahead and rewrite this with the negative out front just so it looks a little bit nicer. This is not necessary, but we've just pulled a negative out of the denominator just to clean it up a little bit. So we still have 3x plus 3 in our numerator, but out of our denominator, we've pulled the negative. So we have 5x plus 3 in our denominator, and then the entire fraction is negative. And then we already figured out the domain because we know that we can't have x equal to negative 1 because it makes g of x undefined, and we cannot have x equal to negative 3/5. And if you actually look at this, the reason that we cannot have x equal to negative 3/5 is because if you plug negative 3/5 into our new function here, you get a 0 in the denominator, which is exactly what we don't want. So in order to figure out how to do that, you actually take the value where it's undefined, which would be 5, and set that equal to your g of x function and solve. Okay, you can also be given problems that are set up this way, which is finding the components of a composite function. So let's say that f composed with g is equal to some function h, and h of x is just 3 over x minus 5 squared. And we want to find some functions f and g such that this could be the case. When we actually compose f with g, it results in something like this. So what we kind of want to do is we want to look for the inside and the outside function. And if you look, we definitely have this x minus 5 here. That's going to kind of be our inside function. So we're going to let g of x equal x minus 5. And then we just kind of look at what's left over, which is 3 over something squared. So in order to actually write that out, you write 3 over x squared. And if you kind of think about this, let's just go ahead and look at it in the other sense. Let's say you were given a g of x and an f of x like this, and you wanted to find f composed with g of x. So if you wanted to find f of g of x, that means that we would take x minus 5, and we'd plug it in wherever we see an x. So we'd get 3 over x minus 5 squared, which is exactly what we started with, so that means that we did a good job defining these functions. It's possible to kind of accidentally assign them in the opposite order, so to make this one f of x, this one g of x, if you go ahead and check it, that will kind of determine whether or not you did it correctly. Okay, let's move on to section 6.2, which is about one-to-one and inverse functions. So we're going to start with some kind of one-to-one function here, which kind of shows that for every x we have one y and so on. And if you look over here, we have different x's that are all going to kind of the same y. So we have kind of, you know, different types of relationships here. So a definition of a one-to-one function is if any two different inputs in the domain correspond to two different outputs in the range, then the function is going to be one-to-one. Meaning that if x1 and x2 are different inputs, then f of x1 cannot equal f of x2. So if we take a look at these, this first one is one-to-one because each value of x in the domain has one and only one image in the range. No y in the range is the image of more than one x. This one's not one-to-one because we have different x's, but we have the same y 2 different times. And this one is not one-to-one. It's also not even a function because we have the same x value that has 2 different y's. This, if you recall from previously, is actually just not even a function. Okay, so if we take a look at this, we can kind of present functions in different ways. It could be listed as maybe a number of points, maybe an equation, maybe some kind of representation that looks like this. So if we look here, we have the following function. It represents the age of 5 males. So we have 5 male ages, and then their HDL, which is their good cholesterol, milligrams per deciliter. So we have someone with the age of 38 who has a HDL cholesterol of 57. And if you look down here, this is kind of where we have something a little different. We have a person that's age 55 and a person age 61, both going to an HDL cholesterol of 38. This function is not going to be one-to-one because of these two people. So these two different inputs have the same output. We need each input to have its own output. So this one is not a one-to-one function. It's a function, but not a one-to-one function. All right, if we take a look at this example down here, we have -1, -2, 0, 1, and 2. No repeating x's, which is good. And if we look at the y's, we have values of 6, 3, 2, 5, and 8. Again, no repeating values. So this function is going to be one-to-one because there are no two different outputs that correspond to the same, or sorry, no two inputs that correspond to the same output. Now, another way to test for one-to-one function is from a graph, and you can use the horizontal line test. So hopefully you remember the vertical line test. That was the one where we took our vertical line and we moved it across our graph. And if it only hit our graph in one place every time we moved it, then we had a function. Now, horizontal line test allows us to see if we have a one-to-one function. So if we take a horizontal line and we pass it across our function, it should only hit in at most one point. If that's the case, then it's one-to-one, but if not, then it's not. So if we take a look at this here, we have something that's not one-to-one because when we take this horizontal line and we draw it through here, it hits in two different places. And the reason for that is that because f of x1 is equal to f of x2. If you look at these have the same y values, but x1 is not equal to x2, so that means that f cannot be a function because we have two different inputs for x that are yielding the same output for y. So let's look at these graphs here. You should know what x squared and x cubed already look like, and we want to determine whether those functions are one-to-one. So if you look at the graph of x squared, hopefully you remember this is just a nice little parabola here. Goes through the origin, has points 1, 1, -1, 1, and we have this line y equals 1. Horizontal line is going to intersect the graph twice. So if we look at our line y equals 1, it hits it twice. Okay, so this is not a one-to-one function. But if we take a look at x cubed, we have our nice little curve here. Kind of looks like that sideways S. This is f of x equals x cubed, or g of x, sorry. And if we look at horizontal lines, we can draw a bunch of horizontal lines, and each time they're only going to hit our graph one time. So that means that g is going to be a one-to-one function. So there's a nice theorem here. We can say that a function that is increasing on some interval I is one-to-one on that interval. If a function is decreasing on a certain interval, then it's also one-to-one on that interval. It's when it changes from increasing to decreasing that we have things that are not one-to-one. So let's suppose now that f is a one-to-one function. Then to each x in the domain of f, there is exactly one y in the range, which we already know. Every x corresponds with one y. And to each y in the range, there is exactly one x, because we know it's one-to-one. So the correspondence from the range of f back to the domain is called the inverse function. Now, this is kind of an important concept, and we're going to do it from kind of easy examples and then also from equations in just a minute. So let's say that we want to find the inverse of the following function. The domain is going to be all these different states that are listed: Indiana, Washington, South Dakota, North Carolina, and Tennessee. And then the range is going to be the populations: 6.2 million, 6.1 million, 0.8 million, 8.3 million, and 5.8 million. So we want to go ahead and state the domain and the range of our inverse function. So finding the inverse in this case should be very easy. all you have to do is interchange the elements of the domain with the range. So we just have to flip them around. So instead of going from Indiana to 6.2 million, we go from 6.2 million to Indiana. So we know that the domain of our inverse is going to be the actual values here, the 6.2, 6.1, 0.8, 8.3, and 5.8, which have been written in ascending order for you. And then the domain, or sorry, the range of the inverse is going to be Indiana, Washington, South Dakota, North Carolina, and Tennessee, because those are all of our outputs. So we have our inputs, which are our population, and our outputs, which are the states. So if you notice, the domain and the range actually flip-flopped. So the domain used to be Indiana, Washington, South Dakota, North Carolina, and Tennessee. That is now our range. And the range used to be 6.2, 6.1, 0.8, 8.3, and 5.8, and that is now our domain. So domain and range, when you find the inverse of a function, actually flip-flop from one another. The domain becomes the range becomes the domain. So let's go ahead and find the inverse of one more function here where we just have a list of points, and we want to state the domain and range of the function and its inverse. So the inverse is just found by flipping the x's and the y's. So all we have to do is, instead of having -5, 1, we have 1, -5. So we just flip our x's and our y's. 3, 3, and 0, 0 are going to look the same because when we interchange them, the numbers are exactly the same. Instead of 2, -4, we have -4, 2. And instead of 7, -8, we have -8, 7. So if we want to find the domain of the original function, we just look at the x's, which are going to be -5, 3, 0, 2, and 7. And whoops, if we want to look at the range of our function, all we have to do is look at the y values, and they're written in ascending order, so let's find them in that order. -8, -4, 0, 1, and then 3. Now, this range is going to be the same as this domain. So if we look at the domain for this function down here, it's going to be all of the x's, which are going to be -8, -4, 0, 1, and 3, exactly the same as the range that we just found. And then the domain of the function is now going to be the range of the inverse. So if we look at the original domain, -5, 3, 0, 2, and 7, if we look at the range of our new function, again, it's -5, 3, 0, 2, and 7. So if we take a look at just kind of another way to represent this, we have the domain of f corresponding to the range of f. This means that the domain of our inverse is actually over here, and the range of our inverse is actually over here. So this blue function is our f, this one is our inverse. So f inverse is how you would read this. It's f with a little -1 as the exponent kind of thing. So domain of f is range of the inverse, range of f is the domain of the inverse. So they just flip-flop. That's all you have to remember with that. Now, if we want to verify that something is an inverse, let's say we have g of x equals x cubed, and g inverse of x equals cube root of x. All we have to do is plug one into the other and make sure that it's x, and then do it the other way around. Okay, so all we have to do is take our original function, g of x, and plug it into the inverse. So we end up with cube root of x cubed because we took our g of x function and we plugged it in where we had our g inverse function. And the cube root of x cubed is just going to be x for all x's in the domain. And then if we take our inverse function and we plug it in to g of x, so we have cube root of x cubed, we're going to get just x for all x's in the domain of g inverse. So that one works. So let's look at this right here. We have f of x equals 3 over x plus 5, and f inverse equals 3 over x minus 5. We want to find for what values of x is f inverse of f of x equal to x. So we want to note that the domain is x not equal to -5, and the domain of g is going to be x not equal to 0. Because when we plug 0 in to our f inverse function, it's going to be 0. And when we plug -5 into our f of x function, again, denominator is going to be 0, which causes all kinds of issues. So if we're finding f inverse of f of x, all we have to do is take 3 over x plus 5 and plug it into our inverse function. So we have 3 over x plus 5 minus 5. And we need to make this look a little bit nicer. So we multiply by x plus 5 in our fraction. So we end up with 3 over x plus 5 over 3 minus 5. And if you actually cancel some things, the 3's are going to cancel, and we're left with x plus 5 minus 5, which is just going to be x, provided that x is not equal to negative 5, because that's a restriction that we need to put on our domain. Now f of f inverse of x is going to be taking 3 over x minus 5 and plugging it into our original function. So we take 3 over x minus 5 plus 5, and we want to make this look a little nicer, so we get 3 over x, and if we go ahead and multiply by the reciprocal, we're just going to get x as this one right here, which is also good, because when you're verifying inverses, that's how you check it. If it's equal to x, when you plug one into the other, and then vice versa, it's going to be an inverse function. And then for this one, we have to kind of put this caveat here, provided that x is not equal to 0, because if x equals 0, it makes our denominator 0. Okay, now if we take a look at this, we have a function y equals x. It just goes through the origin. You guys should know what this looks like. Creates a 45-degree angle with your origin. It's just a line where all of the y's and the x's are the same. So it goes through point A, B, B, and so on. Now, if we have a point AB in an original function, our blue point here, if we wanted to find the inverse, we would just interchange those values. So we'd have BA. So we look right here. And if you actually take a look at this, if we took this point and we reflected it around the line y equals x, we would end up with this point over here. So what we can say is that the graph of a function f and the graph of its inverse, f inverse, are going to be symmetric with respect to the line y equals x. So if we look at this graph right here, we have an original function y equals f of x. This is the blue function right here. We have several points, a1, b1, a2, b2, a3, b3. And then we've drawn the line y equals x right here. And then if we take each of our points and reflect it around this line, we end up with b3a3, b2a2, b1a1, and so on, which is kind of this pinkish reddish line down here. And if we connect these, we can see that we have the graph of the inverse function. So if we take this graph right here, basically this blue graph, and we flip it around this line right here, we're going to end up with our inverse function. So we have a graph here, it's a one-to-one function, and we want to draw its inverse. So probably the easiest way to do it would be to either draw the line of y equals x and then go ahead and flip your graph around it, or to go ahead and pick some of the points that you have, take their inverses, and then graph those. So if we look here, instead of -2, -1, we're going to have -1, -2. So if you look at that graph, -1, -2, that's going to be down here. Instead of having -1, 0, we're going to have 0, -1, which is going to be right here. And then instead of having 2, 1, we have 1, 2, which is going to be up here. And all we need to do is just connect these lines, and we're given our function, or the picture, the graph of our inverse function. And if we take a look, we have the line y equals x drawn here as well. You'll notice that anywhere that the blue line crosses this line y equals x, the pink line is going to cross in the exact same place. This should always happen. And then you should also notice that if we take, for instance, this part of the blue line and we flip it across the y equals x line, we end up with this piece over here. And then if we do the same thing with this piece, this blue piece right here, we end up with this pink piece right here. Okay. Now let's say we want to find the inverse of this function here, f of x equals 2x plus 3, and then we want to go ahead and graph them on the same coordinate axis. So there are several steps involved with finding the inverse, so we're going to go through a couple of examples like this. So the first thing you always want to do is, instead of writing it as f of x, you want to write it with y. And then what you're going to do is interchange the values. So if you take a look, the original is y equals 2x plus 3. And then what we want to actually do is interchange the values of x and y. So instead of putting y here, I'm going to replace it with an x. And instead of putting x here, I'm going to replace it with a y. So I really have x equals 2y plus 3. So all I do is I rewrite my original with a y instead of f of x, and then everywhere I see an x, I put a y, everywhere I see a y, I put an x. Then step 2 is, if it's possible, to solve the implicit equation for y in terms of x to obtain the explicit form of f inverse. So if we take this and we're just trying to get y by itself, if you think about it, if you subtract 3 from both sides, we'd have 2y equals x minus 3, and then we should divide by 2, so we should get y equals 1/2 times the quantity x minus 3. So if we want to write it as our inverse function, we just write it as f inverse of x equals 1/2 times x minus 3, and that would be our answer there. And then we want to go ahead and check the result by showing that f inverse of f of x equals x and f of f inverse equals x. So if we take a look at this, if we take, let's see, our original equation, which is 2x plus 3, and we plug it into our new equation for x, we have 1/2 times 2x plus 3 minus 3. And if you actually simplify this a little bit, you're just going to get x for that one. Okay. And now if we take this equation, this 1/2 times x minus 3, and we plug it into the original, we have 2 times that whole equation plus 3. The 2 and the 1/2 are just going to cancel. We're going to be left with x minus 3, x minus 3 plus 3, which is just going to be x. So this one works. And if we look at the graphs, this is pretty easy to see as well. 2x plus 3 is our original line. That was our blue line here. We had a y-intercept of 3, a slope of 2, so we went up 2 over 1. And then if we look down here, they hit at the same point on this y equals x line, but this one has a slope of 1/2, okay? And instead of having an intercept at positive 3, it goes through negative 1.5, which is right here. And then we go up 1 over 2, and so on. So the general procedure for finding the inverse is to go ahead and write f of x as y, then interchange the variables x and y, and this equation defines the inverse function implicitly, and if possible, we want to solve the implicit equation for y in terms of x to obtain the explicit form. So we want to get y by itself, basically, and we want to write it as f inverse instead of y. And then we want to go ahead and check our result to make sure that it works. So let's look at one more example of this. The function f of x equals 2x plus 1 over x minus 1, where x is not equal to 1, is going to be 1 to 1. So we want to replace f of x with y, so we just write it as y equals 2x plus 1 over x minus 1. And then we interchange our x and our y's. So instead of y, we write our x here. Instead of x's on this side, we write y's. So we have x equals 2y plus 1 over y minus 1. And then we solve for y. So if we multiply both sides of our equation by the denominator, we get x times y minus 1 equals 2y plus 1. And then we distribute, so we get xy minus x equals 2y plus 1. And then we get everything that's attached to a y on one side and everything else on the other side. So we take this 2y and we subtract it, and we take this negative x and we add it. So we get xy minus 2y equals x plus 1. And then we can factor out a y. So we have y times the quantity x minus 2 equals x plus 1. And then we divide both sides. So we get y equals x plus 1 over x minus 2. And we rewrite this as f inverse of x equals x plus 1 over x minus 2, where x is not equal to 2. So I just want to go through this process one more time, because anytime you have a fraction, it's going to kind of turn out the same way. What you want to do first always is to multiply by the denominator to get your fraction to go away. And then you want to distribute everything. And then you want to get everything that's attached to a y on one side and everything else on the other side. And then you're going to factor out a y, and then you're going to divide. So it's always kind of the same process. Once you do a couple of examples, this isn't really something you need to memorize, it's just something you need to understand. It's just solving an equation, but the equation just doesn't look very nice, that's all. But once you've done a couple of these, you'll be fine with them because it's always kind of the same process. So if we actually check this, this is really, really nasty. I would not actually recommend probably checking these once you have the fractions, because there are more mistakes that you can make in the check than there are in the original question. But what I would suggest doing is taking your answer for your inverse and finding the inverse of that and making sure that you end up with the original. This will kind of make sure that you didn't make any sort of silly mistakes along the way. And I actually think it's a little easier to go ahead and go through the same process that we just went through instead of going through kind of this nasty looking check here. So kind of a summary of this section is that if a function f is 1 to 1, then it's going to have an inverse function, f inverse. The domain of f is going to be the range of the inverse, and the range of f is going to be the domain of the inverse. To verify that f inverse is the inverse of f, we plug one function into the other and make sure that it's x, and then we also do that the other way around. And then the graphs of f and f inverse are going to be symmetric with respect to the line y equals x. Okay, so the last section that we want to cover is section 6.3, which talks about exponential functions. So first thing you want to know how to do is how to actually use a calculator to evaluate these. Now, this is really easy once you know how to do it, but you have probably one of two keys. On your calculator, which you're going to want to grab at this point, you either have an x to the y key or a caret key. Now, the caret is a little more common, but either one is okay. So what you actually do when you're plugging these in is you're going to hit 2 and then either your x to the y key or your caret key and then 1.4. Now, it's always possible that you have what I like to call a backwards calculator where everything is kind of reversed. And so if you're not getting the answers that we're going to show here, you may want to try putting the exponent in first and then hitting your key and then hitting your 2, which is kind of the backwards calculator. But just make sure you're able to get some of these answers. So when you do 2 to the 1.4 power, you should get 2.639. So I'm going to give you a second to try that. Make sure you're able to get this answer. Okay, so hopefully you got that. And then if you actually try some more of these, you could do 2 to the 1.414 power, 2 to the 1.41, 2 to the 1.4142, and 2 to the square root of 2 power. So all of these values right here are very close to square root of 2. Square root of 2 is irrational though. And if you do this, you're going to get 2.665144143, and this is rounded. Okay, so this is not an exact answer. Square root of 2 is irrational. When you want to put this into your calculator, you do it pretty much the same way. Once you do your caret key, in order to just be safe, you might want to put an extra set of parentheses before doing your square root button. Okay, and if you have a backwards calculator, you might have to work with this a little bit to figure out how to do that. Okay. We want to go through some of the laws of exponents, okay, so that we can actually solve some equations, which we're going to be doing in next week. But if we take a look, we have a to the s power times a to the t power. That means that we can take a to the s plus t power. So when you've multiplied and you have the same base, you can actually add the exponents. Now, when you've raised it to a power, so if you have a to the s to the t power, if you have a power to a power, then you multiply those two numbers. So this becomes a to the st power. Now, if you have two things in parentheses here and you have one exponent outside, you can actually distribute the exponent. So this is going to be a to the s power times b to the s power. One other important thing to note is if you have 1 to any power, it's just going to be 1. And then over here, if you have a to the 0 power, that's just going to be 1 as well. And you don't need to memorize this. This you could always put in your calculator. And then one kind of important one here is with negative exponents. So if you have a to the negative s power, what you can actually do is you can make the power positive. You can make it a to the s power, and you can put it in the denominator. So you have 1 over a to the s power. Or alternatively, you could factor this out. So you have 1 over a to the s power like this. So let's look at this introduction to exponential growth. Let's suppose that a function f has the following two properties. The value of f doubles with every 1 unit increase in the independent variable of x, and the value of f at x equals 0 is going to be 5. So we know that f of 0 is equal to 5. So if we look at this table of values, we're going to have values of 0, 1, 2, 3, and 4 for x, and we know that it's going to start at 5, and then every 1 unit increase, it's going to double. So we're going to go from 5 to 10 to 20 to 40 to 80, because each time it's actually doubling. So what we actually want to find is we want to find an equation. And if you think about a way that we could write this, we know that f of 0 is going to be 5. We know that f of 1 is going to be 2 times f of 0. So we're going to take 2 times 5. Or I could rewrite this as 5 times 2 to the first power. Now f of 2 is going to be twice of f of 1. So we're going to take 5 times 2 squared. And then for f of 3, we're going to take 5 times 2 cubed. And then for f of 4, we're going to take 5 times 2 to the fourth. So hopefully you can notice that there's a pattern. If you have f of x, that means that we're going to take 5 times 2 to the x power. So an exponential function is just one that's in this form here, where we have f of x equals c times a to the x, where a is a positive real number, so a is greater than 0 but not equal to 1, and c is not equal to 0 and is a real number. The domain f is going to be the set of all real numbers. The base a is going to be your growth factor, and because f of 0 equals c, we call c the initial value. So c is the initial value, a is the growth factor. So let's determine first whether these functions are linear, exponential, or neither. And then for those that are linear, we're going to write an equation. For those that are exponential, we're also going to write an equation. So for each function, what we need to do is we need to compute something called the average rate of change, which you guys should know how to find. This is the same as the slope. And then we also want to find the ratio of consecutive outputs. Now, if the average rates of change are all the same, then the function's linear. If the ratios of the consecutive outputs are the same, then the function's going to be exponential. And then if neither of those are true, then it's not exponential or linear. So let's take a look at this one. We have -1, 0, 1, 2, 3. We have y values of 5, 2, -1, -4, and -7. So to find the average rate of change, we just take change in y over change in x. I'm not going to spend a ton of time on this because hopefully you know how to find slope right now. At this point, because you've done it a bunch of times, you're going to have 2 minus 5 over 0 minus -1, which should give you -3. And then you're going to do the same thing the whole way down. -1 minus 2 over 1 minus 0 gives you -3, -3, and -3. Now, since these are all the same, this means that you have a linear function. We can also just look at the ratio of consecutive outputs so that you get used to it. And all you have to do is just divide. You take the consecutive y values, basically. So we take 2 over 5, -1 over 2, -4 over -1, and -7 over -4. And those are our ratios. So these are obviously not the same. Average rates of change, though, are the same. So that means that our function is going to increase by -3 for every increase in x. Okay, so it's going to actually decrease. The slope is going to be -3 because that's the value that we found for our average rate of change. And then the y-intercept is just the value when x equals 0. So if we look over when x equals 0, we know that y is equal to 2. So our y-intercept is going to be 2. So in order to write the linear function, we just have f of x equals -3x because our slope is -3, plus 2 because 2 is our y-intercept. Now let's take a look at this example here. We have x values of -1, 0, 1, 2, and 3, and we have y values of 32, 16, 8, 4, and 2. So if we take a look at the average rates of change, what you'll see is if we take 16 minus 32 over 0 minus -1, we get -16. And if we calculate the next one, we get 8 minus 16 over 1 minus 0, you get -8. These two are already not the same, so you do not need to keep calculating the average rate of change. Once you know that these two are not the same, you know that you cannot have a linear function, because in order to have a linear function, the average rates of change all have to be the same. So now what we do is we take a look at the ratios. So we take 16 over 32, that's going to reduce to 1/2. 8 over 16, also going to reduce to 1/2. 4 over 8 is 1/2, and 2 over 4 is 1/2. So since these are all the same, we know that we have an exponential function. Now, if we take a look here, we know that the function is not going to be linear, and then we know that the ratio of consecutive outputs for a 1-unit increase is going to be 1/2. Now, because the ratio is consistent or constant, we know that the function is going to be exponential. The growth factor is going to be this factor right here, the 1/2. And then if we look for the initial value, we're looking when x equals 0. And if we look at when x equals 0, we have y equals 16. So we know that our function is going to be 16, which is our initial value, multiplied by 1/2, which is our growth factor, raised to the x power, because we know that that is kind of the general form of an exponential function. We have our initial value multiplied by the growth factor to the x power. Okay, let's do an example here where we have to graph an exponential function, so you can start to see what these exponential functions actually look like. So if we have f of x equals 2 to the x, if we plug some values in, if you do in your calculator 2 to the negative 10 power, you're going to get a number very, very close to 0. 2 to the negative third power is going to be 1/8, still pretty small. 2 to the negative second power is going to be 1/4. 2 to the negative first power is going to be 1/2. Anything to the 0 power is just going to be 1. 2 to the first power is going to be 2. 2 squared gives you 4. 2 cubed gives you 8. And 2 to the 10th gives you 1024. So if we look at a graph, we're not going to plot all of these points, but we're going to plot kind of the important ones, which would be 0, 1, negative 1, 1/2, some of these fraction ones so we can see what's happening here, and then 1, 2, and 2, 4. So we have something that's increasing like this, and then we have an asymptote at y equals 0. So the general properties of an exponential function where you have f of x equals a to the x, where a is greater than 1, is that the domain is going to be the set of all real numbers, meaning that we can plug whatever we want in for x and we're going to get something out for y. But then if you look at the range, it's going to be the set of positive real numbers, because if you look, we have an asymptote here and all of our y values are positive. Now there aren't any x-intercepts and the y-intercept is just 1. The x-axis, which is the line y equals 0, is going to be some horizontal asymptote, okay, and we're going to talk more about asymptotes later in the class. And then f of x equals a to the x, where a is greater than 1, is going to be an increasing function, and it's going to be 1 to 1 as well. And then the graph is also going to contain the points 0, 1, 1a, and negative 1, 1 over a. Now this is not something you need to memorize, because if you need to actually pick these points, I would go ahead and use your equation and find the actual values by plugging in. Now the graph is going to be smooth and continuous, just like polynomials, without any corners or gaps here. So it's going to look something like this nice little smooth curve here. Now let's say we want to graph this exponential function, f of x equals 1/2 to the x power. Now I have full confidence that you guys could plug in values and figure out what your y values are, and you could plot the points and you'd get something like this, because you have 0.01 still, and then we have negative 1, 2, 1, 1/2. So the whole thing is kind of flipped over, and we still have this asymptote at y equals 0. So if you think about it for just a minute, if you have y equals 2 to the x, which was the original graph that we had, and then you change that by replacing x with negative x, we know that when we replace x with a negative x, we're actually reflecting around our y-axis. So what we have here is 2 to the negative x power. Now, this is actually going to be the same thing as 1/2 to the x power, because if you recall, anytime you have a negative exponent, you can actually just make it positive and move it to the denominator. So this is going to be 1 over 2 to the x power. So this equation right here, this y equals 1/2 to the x power, is just a transformation of this graph here of y equals 2 to the x. But we also have a set of properties that we can use so that we don't have to always be flipping this around, which would be the function f of x equals a to the x, where a is a fraction between 0 and 1. So the domain is still going to be all real numbers, range is going to be all positives, aren't any x-intercepts, the y-intercept is the same, it's just 1. We have the same horizontal asymptote, but the big kind of different thing here is that we have now a decreasing function that's 1 to 1 instead of an increasing function. And then our points are all kind of flip-flopped around, so it's going to contain 0.01, 1a, and negative 1, 1 over a. And again, it's smooth and continuous, so it looks very similar to the previous one, it's just decreasing instead of increasing. Okay, so let's look at the graph of this here. We have f of x equals 2 to the negative x minus 3, and we want to determine the domain and the range and the horizontal asymptote. So let's start by sketching a graph of our base function, which is going to be y equals 2 to the x power, which is just going to look something like this. We just graph this here. And then we know that we've replaced x with a negative x, which means that we need to reflect around our y-axis. So all we've done is we've taken our original graph and we've just flipped it around. And then what happens is we've subtracted 3, which hopefully you remember your transformations. I had mentioned in other videos that they just continue to pop up over and over and over again. So if you're still not comfortable with transformations, I would make sure that you practice until you are comfortable. But this minus 3 is going to shift your graph down by 3. So if we take this graph that we have in the middle here and we just shift it down 3, we're going to end up with this graph right here. And one important thing is that the asymptote actually moves with it. So instead of staying at y equals 0, if we shift it down, it's going to move as well. So it's going to be y equals negative 3 as our actual asymptote. And then the domain is going to be all real numbers, and the range is going to be from negative 3 to infinity, not including negative 3 since we have an asymptote there. Now, one other definition is this number e, which maybe you've seen before, but I want to kind of talk about this very quickly, which if you're going on, you will see this again, okay? But it's defined as the number that the expression 1 plus 1 over n to the n power as n approaches infinity. And in calculus, this is going to be expressed using limit notation. So it's going to be the limit of 1 plus 1 over n to the nth power as n approaches infinity. That is how we define e. And the thing that you want to keep in mind is that e is just going to be a number, okay? It's around 2.72, okay? Kind of like pi. It's just an irrational number. It's defined as this, which you don't necessarily need to know, but you do need to know how to find the e button on your calculator so that you can evaluate things, okay? And we're going to use this when we're solving some exponential equations and logarithmic functions. It's going to be pretty helpful. So it's important that you know how to actually find your e button on your calculator. So you should have a little button that it should have a lowercase e. It's probably next to kind of where the logs are or the natural log. Okay, so you might find that and then be able to find your e to the x button. But if you actually find it, if you evaluate some things, if you do e to the negative second power, e to the negative first power, e to the 0 power, e to the first, and e squared, you're going to get a bunch of points here. And we can look at the graph. Now we know that e to the first power is somewhere around 2.72, which is not a fraction. Okay, it's going to just be a number that's greater than 1. So that means that we're going to have some increasing function here. So this is going to look just like our graph of y equals 2 to the x power, except it's going to just grow a little more quickly, okay, and it's going to be a little bit flatter over here. Okay, so let's say that we want to use some transformations now with f of x equals negative e to the x minus 3 power. So we start with our original graph, which is y equals e to the x. And we multiply by negative 1, which means that we reflect around our x-axis. So we've actually taken our graph and we've just flipped it upside down. And then we replaced x with x minus 3, which hopefully you recall that the minus 3 actually shifts the graph to the right by 3 units. So we just take this graph and shift it to the right 3. So we end up with this right over here. You'll notice that the asymptote did not move at all because we didn't shift it up or down. Okay, now one kind of important property is that if you have a to the u power equal a to the v power, then we know that u has to equal v. So we're going to solve some kind of simple exponential equations in this section, and then later in the chapter we're going to do some that are a lot kind of nastier looking. But let's start with this one right here. 2 to the 3x minus 1 equals 32. So what you want to do is you want to rewrite these so that they have the same base, okay? So if you think about the number 32, you probably want to get comfortable with some of the powers of 2, 3, and 4 just so that you're able to recognize them. And if you think about it, you know 2 squared is going to be 4, 2 cubed is going to be 8, 2 to the 4th is going to be 16, and 2 to the 5th is going to give you 32. So instead of writing this as equals 32, we write it as equals 2 to the 5th. And now that we have the exact same bases, what we need to do is we need to actually set the exponents equal to one another. So we just ignore the bases and we just have our exponents, which are 3x minus 1, equal to our 5. So we have 3x minus 1 equals 5, And then we add 1 to both sides and divide, so we get x equals 2 here. And before we do the next one, I would highly recommend that you check this because it's really easy to check. If you take 2 and you plug it into the original, 3 times 2 minus 1 is going to give you 5. And in your calculator, if you do 2 to the 5th power, you're going to get 32. So that one works. Now this one is going to be the same idea, except this one just looks a little not as nice, okay, and it has e's in it, but that's not a big deal. We just need to rewrite this, okay, so if you notice on the right-hand side here, instead of writing e to the negative x to the negative 4 power, we multiplied these two to get the negative 4x power, and we wrote it over this one right here. So if e to the negative 4x over e to the 3x, and then hopefully you remember, if you have powers here, you're going to subtract because we have the same base here. So we can rewrite this as e to the negative 7x power because we have negative 4x minus 3x. So we have e to the 2x minus 1 equals e to the negative 7x. Now that we just have e's as our bases, we can drop the bases and just look at the exponents. So we have 2x minus 1 equals negative 7x. And if you solve this, you get x equals 1 over 9. This one is not going to be as easy to check as the other one just because you have kind of a nastier function to begin with, but you could definitely plug 1/9 into your calculator in here and on the right hand side and make sure that they both match. They won't be nice numbers, but they should be the same kind of not so nice number. So if we look at a summary of the properties of an exponential function, we have kind of these two different looking graphs here. We have f of x equals a to the x, where a is greater than 1. That's going to be increasing. Okay, it's going to have a domain from negative infinity to infinity and a range from 0 to infinity, not including 0. We don't have any x-intercepts, but we have a y-intercept at 1. We have a horizontal asymptote at y equals 0. And it's increasing. It's smooth and continuous, so it's going to look something like this. Now, if we have something where we have a between 0 and 1, so a equals 1/2, for example, or 1/3, something like that, we're going to have a decreasing function. So it has pretty much the same, it has the same domain, same range, same y-intercept, same horizontal asymptote, but this one is decreasing. And it's going to also be smooth and continuous. But this one is going to approach the horizontal asymptote as x reaches infinity, whereas this one up here approaches the horizontal asymptote where as x reaches negative infinity. And then the other thing we talked about was the fact that a to the u power equals